Notice that what is driving our understanding of the edge of the solar system is not the latest cutting-edge technology, but an old machine. It is the apostle of mankind, the drifting plane of the universe, or perhaps the tombstone of the future of human civilization. That look back that shocked the world, the photos that shocked people, the information that opened up unknown areas for mankind, promoted mankind's understanding of the solar system, and that figure that will never return. Ironically, its onboard computer has less memory than a car key. To this day, it still uses 8-track tapes from the 1970s. This is older than most people born in the 1970s. This is where the conundrum of deep space exploration lies. Huge distances and extremely long travel times can mean today's most powerful equipment becomes obsolete before it reaches its goal. The spacecraft that set the record were, of course, the nearly 45-year-old Voyager 1 and Voyager 2 probes. They became the first human-made objects to enter interstellar space. Today, let's explore the technology of the Voyager probe and learn about the most forward-looking and successful mission in the history of space exploration. In 1977, 2 explorers embarked on what may be the grandest expedition in history. After a journey of 47 years and 24 billion kilometers, they are still delivering amazing new discoveries about the universe to us in interstellar space. Voyager 1 and 2 were more than just a bunch of instruments and circuit boards. They were the embodiment of the human spirit of exploration. Not only did they capture the majestic views of the solar system's giant planets and their moons, they also won the hearts of generations of people on Earth. These 2 detectors have gone further than any man-made object and are true pioneers and innovators. They capture something we've never seen up close before. These scenes may never be seen again in the future. Interestingly, it's not the latest technology that's advancing our understanding of the edge of the solar system, but those old machines. They are older than many of the people watching this video. This is a major challenge in deep space exploration. The huge distances and long travel times mean even the most cutting-edge technology can become obsolete over time. The original mission of Voyager 1 and 2 was not to explore interstellar space. Rather, it was intended to explore the extremely large moons of Jupiter and Saturn. This is due to a rare planetary alignment that only occurs every 176 years. After completing the exploration of Jupiter and Saturn, the mission team added flybys of Uranus and Neptune to the probe's goals. When these goals are also accomplished, the travelers began their interstellar mission. The aim is to explore the edges of the sun's sphere of influence and beyond. This final journey will take the 2 detectors out of the ecliptic plane, travel to unexplored parts of the solar system, traveling through more densely, a hotter heliosphere, finally entering interstellar space. How do these machines manage to accomplish so much beyond their original mission? This is due to the old one's incredibly effective technique. Scientists made some forward-thinking design choices, enabling probes to travel far beyond their original targets. Each detector is equipped with a long-lasting radioactive thermoelectric generator. It converts heat generated by the decay of the isotope Fuji into electricity. These generators are capable of producing 157 watts of power during takeoff. Not much, but enough for travelers. Although the power production of radioisotope generators will continue to decline, but it's still enough to keep the detector operational until at least 2025. Each Voyager probe is equipped with 11 scientific instruments. Most of them have redundant designs in case the machine fails, in order to adjust the course and direction. The detector is equipped with a gyroscope for stabilization. There are also reference instruments and 16 police thrusters. Includes 8 backups. These backups played a key role when Voyager 2's main thruster stopped working after 37 years. Its backup thrusters activated after 40 years of inactivity. Works perfectly. Demonstrated superior engineering quality. Travelers also have customized onboard computers. although outdated by today's standards. But it was cutting edge in 1977. The detector's wide-angle and narrow-angle lens cameras are controlled by a computer command subsystem. This subsystem has fault detection and correction procedures. Another key to the Voyager mission's success is their computer system. Each detector is equipped with a computer called the Attitude and Arc Control System. Don't get me wrong, this system is not designed to teach detectors a lesson when they disobey, but to control their posture relative to the Earth. This is crucial, because if there is no correct posture, the detector's high-gain antenna cannot effectively communicate with NICE's deep space network. Think about it. The detector's transmitter is only as powerful as the light bulb in your refrigerator, and they are so far away from us. The radio signal is almost negligible. So, to stay connected, the detector's antenna must always be pointed toward the Earth. The Deep Space Network must also know precisely where they are. Otherwise, each Voyager spacecraft is equipped with a 3.7-meter antenna, used to transmit data in real time. There is also an 8-track digital tape recorder. It can store 536 megabits of data, enough to save 100 photos. While this is a huge improvement over earlier Pioneer detectors, but compared to modern smartphones, its storage capacity still appears to be quite limited. But these digital tape recorders, DTRS, designed to last. They are manufactured by Odetics, capable of processing over 4,000 kilometers of tape without obvious wear and tear. These devices must be able to withstand extremely harsh environments and pass rigorous testing. In fact, Voyager's DTRS has operated for many years without data loss or machine failure, until it was forced to go offline to save power, for a technology that is 12 years earlier than the Internet. This is already remarkable. Durability is a major consideration in traveler planning. In such a grand task, there are many unknown factors. For example, in order to reach Jupiter, both travelers must travel through the asteroid belt. Past. Scientists believe the asteroid belt would destroy any spacecraft trying to travel through it. However, the successful crossings of Pioneer 10 and 11 gave the Voyager team confidence. Fortunately, both probes safely passed through the asteroid belt. We now know it's actually mostly open space, even though the detector's performance exceeded engineers' expectations. As they traveled through the vast space between planets, still facing the challenge of extremely low temperatures in interstellar space, NICE installed multiple heaters to keep the equipment running. But as electricity gradually decreases, some heaters had to be turned off to save energy. When the Cosmic Limits probe's heater was turned off 2 years ago, the temperature plummeted by 70 degrees Celsius. Obviously, we can't send maintenance teams that far. Many people think that the instrument will be damaged, but they continue to operate stably. In fact, the detector can operate for 45 years. This is a testament to their toughness and superior engineering quality. Let's go back to 1977. See how the Voyager probe's journey began. August 20th, NASA launched Voyager 2 from Cape Canaveral, Florida. 2 weeks later, his companion Voyager 1 was also launched. Although both probes are heading to Jupiter, but Voyager 1's trajectory was shorter, faster, so launch later. December 15th, he passed Voyager 2 and left the asteroid belt first. The two probes were tasked with taking a series of stunning photos. This was revolutionary at the time. Shortly after launch, Voyager 1 sent us a photo taken from 11.6 million kilometers away. This was the first of tens of thousands of photos he sent back over the next 5 years. He recorded our blue planet and the moon in the distance, reminiscent of the sight of the Earth rising during the Apollo 11 mission. This photo is hauntingly beautiful, especially when you think about how far this probe has traveled. The budget of this photo, seen so much. As Voyager 1 slowly approaches its first target, Jupiter, we've been waiting for nearly 2 years. He arrived on March 5th, 1979. Amazing speed, 17 kilometers per second. Although Voyager 2 departed early, but arrived later. Because his trajectory gives him more gravitational acceleration from the Sun. Voyager 1 was not the first spacecraft to visit Jupiter. Harold 10 went there 7 years ago, but the pioneers did not capture the public spotlight like the travelers. Voyager 1 captured a panoramic view of Jupiter. These photos are so realistic. It's hard to believe they weren't drawn, or some AI-generated image. In the photo, we can see Jupiter's 2 moons, Io and Europa. We'll learn more about them later. Voyager 1 also recorded its entire approach to Jupiter. A photo is taken every 10 hours, and these photos are connected in series to form a time series movie spanning 27 million kilometers. This gives us a glimpse into Jupiter's atmosphere, which is full of turbulence and rotational motion. Scientists have long suspected that Jupiter's Great Red Spot is a counterclockwise rotating storm. Voyager data confirmed this and revealed that there are many similar storms in the atmosphere. In addition, travelers confirmed the existence of Jupiter's rings and captured their images for the first time. Volcanic activity on Io is one of the biggest surprises of the Voyager mission. Previously, people thought that the surface of Io would be full of impact craters, but Voyager 1 discovered the rings of Jupiter. Volcanoes on Io are volcanic hotspots and lava lakes. These volcanoes are very active and erupt, spewing material and gas up to 100 kilometers into space. Europa is an icy world. Voyager 1 reveals for the first time those strange scratches on its surface. These may be crevasses, and the Voyager data also suggested for the first time that there might be an ocean of liquid water hidden underneath. Before 1979, we only knew that Jupiter had 13 moons. But the Voyager mission discovered 3 new satellites, bringing the total to 16. After Voyager 1 visited Jupiter, it continued its journey. 21 months later, it approached Saturn, this generation ring planet. In November 1980, Voyager 1 approached Saturn for the first time. Its companion Voyager 2 arrived there 9 months later. Before the Voyager spacecraft arrived, our knowledge of Saturn's rings was limited. Thought it only had 5 main rings. But Voyager 1's close flyby revolutionized our understanding. This leap revolutionized us in detail. This leap not only allowed us to see more details, but also allowed us to learn a lot of new knowledge. The Voyager probe also discovered machine rings and gained a deeper understanding of the M ring. The F ring is not a single ring, but consists of multiple curled rings. More importantly, Voyager 1 discovered 2 shepherd moons named Prometheus and Pandora. They maintain the structure of the F ring. The discovery confirms scientists' theories about the shepherd moons and how they maintain the consistency of the ring material around the narrow rings. In addition, travelers also discovered some unusual features on Saturn's wall rings, which look like wide strips on wheels. These characteristics are inconsistent with our previous understanding of the gravitational influence of Saturn's rings, triggering heated discussions in the scientific community. Currently, the leading theory is that these floating bars may be caused by electrostatic repulsion, which separates tiny dust particles from the main body of the ring. However, the Voyager probe also brought us some not-so-good news. Saturn is losing its rings. Due to gravity, the ice particles in the ring are being pulled toward the planet, creating a dust cloud of ice particles. At that time, it was predicted that Saturn's rings might disappear within 300 million years. This discovery inspired more in-depth study of Saturn. The Cassini detector launched in the 1990s was specifically designed for this purpose. It orbited Saturn for 13 years and provided a wealth of information about the ringed planet. The Voyager probes also made new discoveries about Saturn's moons. Before Voyager, we only knew that Saturn had 14 moons, but the Voyager 1 and 2 flybys let us know more. In particular, Pioneer 11 was the first detector to image Pheasant 6 and Pheasant 2. Follow-up by Voyager 1 found that Titan has a dense nitrogen atmosphere. This is the first we've encountered outside of Earth. Daphne 2 shows its strangeness. Not only is it visible from a distance, but it is also ejecting water vapor, forming a huge rain stream of water vapor. These rain streams provide material for one of Saturn's icy rings. After completing the exploration of Saturn and its satellites, Voyager 1's journey is not over. But its path has deviated from the ecliptic plane and started heading directly to interstellar space. Meanwhile, Voyager 2 continues its journey to Uranus and Neptune. This is the first and only time in human history. After visiting Saturn, Voyager 2 continued its interstellar journey. In January 1986, we had a close encounter with Uranus. This flyby gave us a glimpse of Uranus's atmosphere, which is very different from Jupiter and Saturn. It appears unusually calm, with almost no visible cloud features. Moreover, Uranus's axis is tilted 98 degrees. This is quite rare among the planets in the solar system. What's even more surprising is that Voyager 2 discovered Uranus's magnetic field, and this magnetic field is tilted 59 degrees. This means that its magnetic and geographical poles do not coincide. This is completely different from the situation on Earth, and also breaks scientists' traditional understanding of planetary magnetic fields. This polar misalignment causes Uranus's magnetosphere to wobble as the planet rotates. This is also unique in the solar system. Voyager 2 also gained a deeper understanding of Uranus' ring system. More details were revealed and 2 new rings were discovered. It captures images of these rings, showing that they are composed of tiny dust particles, and discovered 2 shepherd moons orbiting one of the rings. In terms of satellites, before Voyager 2, we only know that Uranus has 5 satellites, but its leap has taught us 11 new satellites. This brings the total number of satellites of Uranus to 16. These newly discovered moons provide us with information about their size, valuable data on composition and orbital characteristics. Speaking of Uranus' original satellites, most of them look like a mixture of ice and rock. The surface is covered with impact craters, showing their ancient geological age, especially Titania. Its surface has huge faults and canyons. It is suggested that it may have experienced some geological activities in history. Uranus has the brightest surface of all Uranus satellites. Large-scale geological changes have occurred. Miranda, a small satellite of Uranus, Voyager 2 brought the biggest surprise. January 4th, 1986. Voyager 2 flew past Miranda at an extremely close distance. Deep canyon-like faults on its surface were discovered. These features suggest Miranda has a turbulent geological history. Its surface features are a mix of ancient and young terrain. Shows complex geological activities. After completing the exploration of Uranus and its satellites, Voyager 2 continues its journey to its final planetary destination, Neptune, leaving behind the last impression of Uranus. After 3 years of high-speed travel, Voyager 2 finally arrived at the edge of the solar system on August 25, 1989. Visited distant Neptune, it sent back unprecedented close-up photos of Neptune. It is only 5,000 kilometers away from the planet's north magnetic level. This is our closest encounter with Neptune. This gaseous state contains the most hydrogen in the planet's atmosphere. Voyager 2 also detected unusual high-speed winds on Neptune. Wind speeds near the equator are as high as 1,100 kilometers per hour, showing the extreme dynamics of Neptune's weather system. Even more shocking is that scientists discovered a huge storm on Neptune. known as the Great Dark Spot. It is similar to the Great Red Spot on Jupiter, but the wind speed is faster. It is the strongest wind speed recorded in the solar system. NICE analyst Ken Balinger commented on this in 1989, expressing wonder at the ever-changing scenery on Neptune. Voyager 2 also imaged Neptune's ring system for the first time. Several partial ring structures were revealed. That is the arc. The discovery of these arcs raises questions about their formation and stability, because they appear to be made of incomplete and dusty rings. On Neptune's largest moon, Triton, Voyager 2 also made a surprising discovery. Triton is the coldest known object in the solar system. The surface is full of cracks. There are also intermittent total eruptions. Antarctica is covered with pinkish light ice. Scientists also observed dark rain streams. This could mean the presence of cryovolcanoes. After completing the exploration of Neptune and its satellites, Voyager 2 begins its interstellar journey. At the same time, Voyager 1 has been 600 million kilometers away from us since 1980. In order to save electricity, scientists originally planned to turn off its cameras. But at Carl Sagan's suggestion, Voyager 1 took the famous pale blue dot photo on February 14, 1990. Looking back at the Earth from 6 billion kilometers away, that quote by Carl Sagan profoundly expresses the meaning of this photo. Emphasis on our protection. Voyager 2 is a reflection and revelation on Earth. After Voyager 2 completed its visit to Neptune, it continued towards the edge of the solar system, while Voyager 1 had already begun its interstellar journey. In 1981, Voyager 1 began to deviate from the ecliptic plane, which is the plane of the Earth around the Sun, by 35 degrees to the north. Later, Voyager 2 also deviated from the ecliptic plane, but moved 48 degrees south. This marks their entry into a new phase of traveling to interstellar space. To reach deep into interstellar space, travelers must travel through what is known as the abort impact. This is the region where the solar wind meets the interstellar wind and slows down. Beyond the aborted impact is the heliosphere, where the solar wind becomes denser and hotter. Further outward is the heliopause, the final dividing line between the solar system and interstellar space. It is worth mentioning that even if it passes through the heliopause, it will take Voyager 1 300 years to reach the Oort cloud. While traveling through the heliosphere, the Voyager probes made an astonishing discovery. The Sun's magnetic fields rotate in opposite directions at the poles, and when they meet, they create sheets of heliospheric current, similar to the ripples produced by a stone dropped into water. But at the end of the impact, these ripples are compressed, forming a magnetic field bubble. This is very different from what scientists previously understood. On July 25, 2012, Voyager 1 became the first man-made object to leave the solar circle and enter interstellar space. It advances at a speed of 540 million kilometers per year, crossing a distance of 120 astronomical units from the Sun. This discovery made us realize how little we know about the location of the heliosphere. Some early models even suggested it was near Jupiter, when in fact it was much farther away. At first, NAS was not sure whether Voyager 1 had actually entered interstellar space. Although the detector's data showed a significant increase in plasma density, the number of cosmic rays surged. But Voyager 1 did not detect the expected magnetic field changes, which confused scientists. It took them nearly a year to confirm that Voyager 1 had indeed entered interstellar space. On November 5, 2018, Voyager 2 also joined the ranks of interstellar space at a speed of 490 million kilometers per year. It crossed at 120 Australian dollars from the Sun, and again no changes in the magnetic field were detected. This discovery once again challenges our understanding of interstellar space. These discoveries by Voyager 1 and 2 not only provide us with valuable information about the boundaries of the solar system, it also gives us a deeper understanding of interstellar space. The sun's activity cycle rises and falls every 11 years. And Voyager 2 passed through the heliosphere when sun peak was at its peak. Original models predicted that the heliosphere would change in size over this cycle. But Voyager 2 passed through the heliosphere at the same location as Voyager 1. This suggests that our previous model was wrong. We now suspect that the boundary between the heliosphere and the interstellar medium is much more complex than previously thought, full of volatility. And the detectors themselves are starting to show their age. In May 2022, Voyager 1 began to send some strange signals. If you were a NASA scientist checking telemetry data every day, you'll notice that these signals mean nothing, like a string of 0 or 3,707 numbers. But at the same time, its scientific data is all right. This allows you to rule out signal problems. You check Voyager 1's other systems. I found that the power supply was a little low, but consider it has been traveling for 45 years. This is also expected. Scientists had predicted it might not last beyond 2025. But there is still time. After 4 months of inspection and testing, NASA's team finally identified the problem. Turned out to be Voyager 1 started with an old one. Corrupted computer system sending data, causing the data to become confusing. Once you switch back to the correct computer, the problem is solved. Despite this, as Voyager 1 continues to travel through interstellar space, you may experience more glitches. July 2023. Voyager 2 deviated from its direction towards the Earth due to a series of routine orders. Gene Naser lost contact with him for a time. Fortunately, through the efforts of the Deep Space Network, Voyager 2 readjusted its direction. Communication was restored. Facing the intense radiation in interstellar space, Voyager 1 actually started sending data using an old and faulty computer system. The result is a bunch of garbled numbers transmitted back to Earth. Fortunately, the solution to the problem is also simple. That time the travelers were asked to switch back to a normal computer, everything returns to normal. Although it sounds simple, but it still took several months to actually solve the problem. But the challenges are not over. In November 2023, there was also a problem with Voyager 1's flight data subsystem. As a result, useful scientific and engineering data cannot be returned. Until June 2024, this problem was solved. Voyager 1 is really old. Who knows what other glitches might be encountered in interstellar space? Same. Voyager 2 also encountered trouble in July 2023. A routine command caused his antenna to deviate 2 degrees from the Earth. Just this little deviation, Gene Nas lost contact with him. Fortunately, with the assistance of the Deep Space Network, 37 hours later, we finally reconnected. It is known, one day, the traveler's signal will cease, whether due to malfunction or energy exhaustion. But even if the signal stopped, their journey would still be long. Consider that Voyager may first be approaching a star in the constellation Camels in the next 40,000 years. Voyager 2 will pass by the star Screw 248. In another 296,000 years, it will be close to Sirius. These probes may outlive Earth, continue to roam the galaxy. If travelers encounter an alien civilization, the gold records they carry will tell our story. The sounds and images of Earth were recorded on those golden records. The music of Mozart and Chuck Berry. There are also greetings in 55 languages. Like a distant stranger, show who we are? What is life like on Earth? Although we must wave goodbye to travelers. But this is also a new starting point for human exploration of the universe. Hope this is just the beginning. In the future, we can have more contact with the stars. Thanks for watching. If you have any ideas, welcome to leave a message and share.